So another really key technology that's driving the evolution of virtual instrumentation and graphical system design is FPGAs. We've just really been amazed and surprised at all of the great applications you've been able to do with our Rio products over the last few years. Recently, we've really been turning our attention more towards applications that need to use the FPGA for very high-speed signal processing. So applications like wireless communications or software-defined radio are very demanding, both in terms of performance requirements and in just overall system complexity. Now, to really make sure we were focusing on this problem, we recently created an internal R&D team of communications experts. And their specific job is to make sure that LabVIEW and our hardware is really good for these types of applications. One particular area that they focus a lot of energy on is the easy integration of the very high-performance IP that's needed to use FPGAs for these applications. And so to hear you tell you about some of the work that this team is doing, please welcome Dr. Ian Wong and Young Rao. Morning, guys.
Morning, Mike.
So Ian only joined NI about 4 months ago. I don't think he was expecting to be called up on the NIWeek stage quite this quickly, but since you did join us for this communications team, why don't you tell the audience a little bit about your background?
Sure. Prior to joining NI back in March of 2009, I was actually with Freescale for a couple of years, implementing and standardizing LTE, a next-generation cellular standard. So prior to that, I actually got my PhD in the University of Texas at Austin.
Of course. So tell us about the kind of work that your team is doing.
Sure. Young and I are part of a team that is tasked on implementing advanced prototypes so that we can identify the key requirements to implement the next generation high-performance signal processing and communications applications. So because of my background in LTE, we've actually decided to implement an LTE base station emulator.
Cool. So give us a little bit of information about LTE.
So LTE is the next generation cellular standard following 3G. Over the past 10 years, we've seen a dramatic evolution of cellular standards that allows us to receive much higher data rates from like 500 kilobits per second for a GSM GPRS Edge standard, all the way to 300 megabits per second for an LTE standard, which is set to be rolled out by next year. And because of that amount of complexity, we also need a lot of complexity in our equipment, for example, like a base station, and up to 1 teraops of performance is required in an LTE base station. So, for example, in an LTE base station, processing requires greater than 200,000 2K FFTs per second, a greater than 300 megabits per second turbo decoder, very complex higher layer software, and even backward support to all these other standards that I mentioned.
So you guys are building a prototype that can do all of this processing?
Oh, no, Mike, don't get me wrong.
Okay.
I mean, our team is tasked to kind of exercise our platform. So what we're doing right now is an LTE base station emulator prototype. Basically, it's based on a PXI Express system, at the heart of which is a real-time dual-core controller, where we do our higher layer processing and link control. This then communicates with our IF transceiver, a PXIe 5641R IF transceiver, which is basically an FPGA board with integrated intermediate frequency I/O. This is where we do the complex physical layer processing for our LTE base station transmitter. The IF signals are then fed into our modular instruments RF up converter and then communicating with our device under test. The signals from the device under test are then brought back using the RF down converter to our IF Rio, where we do our receiver processing, and back to the RT controller where we do our performance measurements.
Wow, that's a pretty complicated system. So you're going to show us all this working today?
Well, we've only been working for this for only a couple of months.
Okay.
So for one, we don't have any commercial devices under test yet.
So no LTE phones yet? To test the system.
None yet.
Okay.
I wish we had, though. Right? So basically what we're going to do here is an RF loopback demo where we do the physical layer base station processing on the FPGA, but then looping back to our physical layer user equipment receiver onto our RT target. And we perform some measurements on that signal.
Great. So let's see the application, which is running, right?
Sure. Yeah. So this application right here is the front panel of our base station emulator. On the left, you can see some controls for LTE signals. For example, the RF carrier frequency can be configured. We can configure the bandwidth and the modulation order. The power spectrum here is shown at the receiver side. It's a 10 megahertz bandwidth, and the constellation shows a 16 QAM constellation, and they're all pretty clean. Basically, what we're doing here is we're actually transmitting 32 megabits per second through this RF link.
Cool. So this LabVIEW application, then, not only are you doing the prototype with it, you actually can use it as a design tool where you can explore the operation and the implementation of the algorithms, right?
That is right. So Young can actually move around, for example, the noise standard deviation to see how much it kind of blurs out our constellation, and actually also adjust the signal gain, the digital signal gain of our transmission.
Cool. Now you said that the FPGA is a really important part of the system for all the processing power that you need. Have you guys done a lot of LabVIEW FPGA development?
Indeed, we have done a lot of LabVIEW FPGA development. And basically, this block diagram right here shows us the block diagram of our LTE base station transmitter. In addition to the LabVIEW FPGA IP, which is shown in the yellow blocks, we also have a lot of third-party IP that's very important for me to get up to speed real quickly and implement a base station transmitter. In this case, we're using an IFFT and some sampling rate conversion blocks from Xilinx.
So basically, since you already have the IP available, you want to be able to take advantage of it and integrate it into LabVIEW. So that's a lot of IP integration. Are you a VHDL expert?
Oh, no. I'm not even close to being a hardware guy, Mike. I'm a communications guy. So if I were a VHDL expert, I would have used the LabVIEW FPGA clip node to bring in this third-party IP. Fortunately, the LabVIEW R&D team actually came up with a new node that allows me to bring in third-party IP without me having to know any VHDL at all.
So you're actually able to bring in the Xilinx IP but not having to work in the VHDL directly, so you have this new node. Can you show us how you use it?
Sure. So this block diagram right here is actually the heart of the IFFT, heart of our processing in OFDM, which is an IFFT with cyclic prefix. So this purple node right here is the 2K IFFT I was mentioning, and that actually is Xilinx IP that I brought in natively into LabVIEW FPGA.
Okay, well, I can't help pointing out, though, that LabVIEW already has an inverse FFT for its FPGA. Why didn't you just use the LabVIEW FFT?
Actually, I could have used the LabVIEW FPGA IFFT. However, Xilinx has this very useful feature in their IFFT which automatically adds a cyclic prefix to my signal. This is a very important processing step in OFDM.
Cool. So I would assume, though, that this is the kind of thing that we're learning as we go, and then probably someday this will be part of the LabVIEW FPGA IP as well, right?
Of course.
Right, but for now, it makes sense to just be able to use the IP that you have. So can you show the audience how you actually get the IP into this new node?
Right. The IFFT is quite a complex block, so it'll take us 10 minutes to go through that. Basically, I'll focus on this binary counter right here, which basically is a counter that counts from 0 to 6 and back to 0, because the cyclic prefix lengths actually vary in that manner in LTE.
I see.
So the first thing we need to do is to go into Xilinx CoreGen. So Xilinx CoreGen is this tool from Xilinx that allows me to choose from a variety of IP from Xilinx and configure them according to my needs. In this case, let's configure a binary counter. So basically, we want to set some parameters here. We want the output bit width to be just 3 bits, restrict the count all the way to 6, and also put in a clock-enabled terminal. As you can see in our block on the left, the parameters and the terminals are actually changing as we change the configuration. This is also how it will show up in our LabVIEW FPGA diagram. The next step is for us to click Generate, and then Xilinx will generate VHDL files and the configuration files that we will need later in LabVIEW FPGA. We will not do that right now in the interest of time because we've generated already previously. So let's go back to LabVIEW FPGA and open up a new VI where we can drop in this new node that I was talking about. We basically double-click on that node and simply point to the files that Xilinx has already generated, in this case, our 3-bit counter. And as we click Generate, LabVIEW FPGA actually imports the VHDL, imports the configuration, and actually generates a simulation model, at the same time a compilation NGC file for our LabVIEW FPGA diagram. We go through a few more steps, and finally we have the terminals that as they will show up on our LabVIEW FPGA diagram. By clicking Finish, LabVIEW FPGA then further processing a few more files, and voila, we actually have a node right there in the diagram.
And that's it. Now with this node, you can use that external IP in the LabVIEW diagram, just like any other node. Is that right?
That is right. However, there's a very important feature that we haven't had previously, and it's the ability to do desktop simulation of this IP. Previously, we have to compile and run it and see what happens. Now, with the ability to do simulation, we can actually figure out whether our block is working correctly right off the bat. And in this case, Young has just shown us in a few steps that our binary counter actually performs correctly.
Okay, so not only does this node let you bring in IP, it automatically creates a simulation model so that you can start writing your applications right away, even without targeting the FPGA.
That is right.
That's cool. Now, does this only work with Xilinx IP?
Actually, it can work with any external VHDL as well.
Well, that's great. So I think that's going to really help a lot of our domain expert customers integrate this key IP into their applications for communications and other applications. So great work. Thanks, guys.
Thanks, Mike.